before we proceed, what is the expression for the reaction quotient? Let us now discuss a little bit about the deviation for from the ideal behavior for a say mixture. Now we already discussed the thermodynamics of mixtures, where we discussed Raoults law as well as Henry's law. Now remember, in Raoults law we wrote the chemical potential as mu A star, where mu A, say chemical potential of any component A, and we wrote the star notation to designate that it is in the pure state, like it's a pure solvent, say for example, say pure water. And then of course there was a deviation for the Raoults law, and we wrote it as RTLN PA by P0. That's a correct equation, but that PA by P0 we wrote it to be equivalent to the mole fraction, which was not correct. Now we are writing it, okay fine, let us just define a quantity which will explain everything in the limit of dilute solution, in the sense that this quantity A, small a, will actually describe the behavior over entire range of mole fraction. So that quantity, we call it as activity. So this is activity of an component. In this case, it is activity of A. Now, what do you mean by activity? So in Raoults law, so this was activity. We could actually replace. Activity is nothing but in this case PA by PA star, which was taken to be the mole fraction of A. That was Raoults law. So this activity you can think of as an effective mole fraction in the sense that it's not exactly the mole fraction, because we saw that if I take it to be XA, then in some range it follows Raoults law, but not for all range. And we saw that for a fairly dilute concentration, when we talked about dilute solution, from the solvent's perspective it is okay, but from the solutes perspective it is not okay. So from solvent's perspective, Raoults law was okay, but as we increase the mole fraction of the solute, we saw a huge departure, and that's what was the problem with Raoults law. And now we are saying that everything can be explained with this quantity, which is known as activity. It can be replaced by mole fraction only in the dilute concentration, dilute solution. And so this activity can be thought of as an effective mole fraction, and we can always write this activity is, suppose, some way actually proportional to the mole fraction, and this proportionality constant we write it as something like a Greek letter gamma, and we call this gamma as activity coefficient. So gamma is known as the activity coefficient, and of course you can see that for Raoults law to be valid, gamma should be equal to 1. So what it means is that as the mole fraction of the solvent, let's say I'm keeping A as a solvent and I'll write B as the solute. So if the mole fraction is tending to be 1, the gamma is tending to be 1, so that activity becomes the mole fraction. So that is the concept here. So activity can be, I mean, anything, but like for example in the very concentrated solution, we are saying that there itself it will be proportional to XA, but it won't be equal to XA. It will be equal to gamma A into XA, but that gamma A, now the question is how to calculate the gamma A for the concentrated solution. That we are not going to discuss. We are going to say that it will be still proportional to mole fraction, but all this departure will be now contained within the gamma. If you can make, or if you can come up with a theory which nicely shows how basically gamma A, or the activity coefficient, is going from a value of 1 to something else in a very, very nonlinear fashion, then you can think about that we can actually have a very real situation which can explain everything. So gamma is not actually exactly a constant. It also depends on the mole fraction. That is very, very important. If I take gamma to be, we are saying that gamma tends to 1 when mole fraction is tends to 1, which means actually I cannot take gamma to be 1 for the entire range of mole fraction. When the mole fraction of A is actually, decreasing, or XA is actually decreasing from 1, or we are doing a departure from the pure solvent to the solution thing, we are adding more and more solute to it, then we see that there is a departure. And that departure we can account for if we can adjust the gamma, which means gamma has to be dependent on XA, or mole fraction. It is not exactly a constant. Now we can actually write it in a way like mu A is nothing but mu A star plus RT ln XA plus RT ln gamma A. Now I'm just writing it in terms of activity as XA into gamma A, and remember that this is what we have discussed so far is with respect to the solvent perspective. So it is basically the concept of activity from solvent perspective. We know that from solutes perspective it is very different. And what is the difference? We already know that. Now for dilute solution, which means that we can, when x tends to 1, we can write gamma to be tending to 1, or we can actually write it that the gamma is almost equal to 1, so we can actually ignore this term, and then it reduces to Raoults law, as you can see. So that is the entire concept. And now what happens from the solutes perspective? Now from the solutes perspective, we know that we have to take Henry's law, and that was basically for ideal dilute solution. And then what we are writing here is that is the same way. We can just write it as mu B. We are writing A for the solute, just like here, and we are writing mu B is mu B star plus RT ln PB by PB star, which is basically the activity. Now you see here that this equation is not very correct. We already know that. The reason is the pure solute in a solution, you can actually think that whenever it is a dilute solution, of course for a concentrated solution it will vary a lot, but even for a dilute solution, from the solutes perspective, we see a huge departure. Henry's law, Raoults law is valid from the solvent's perspective. The reason being, in the solution, you can think that it is almost a similar environment, just like in a pure liquid or pure solvent, but from a solutes perspective it is very, very different. So this is not a very correct equation from the solutes perspective. Now you know that we can write it as we already discussed about Henry's law, and Henry's law said that this thing, which is basically PB by PB star, which was approximated to be P by PB P total, and which is of course equal to the mole fraction, which was Raoults law, is not correct if we just take it as PB by PB star. So that thing is not correct. This equating this with this is not very correct for the solutes perspective. And so what Henry told that it can be instead be thought of as some kind of proportionality with respect to the mole fraction. So then we already see that we have to define now the activity, how to define the activity of the solute with respect to all these equations. So we write, remember that activity is nothing but the way we are writing it is as PB by we can write the actual equation in terms of activity, because the way activity is defined is that that equation will explain everything for all range of solute concentration or solvent or the solute concentration. So the real equation will be nothing but mu b is mu b star plus RT ln activity of B. Now this activity of B, again as before, we can write it as activity coefficient plus times the mole fraction, and we can write it as RT ln XB plus mole fraction, which is we can write actually AB is gamma B into XB. Now this gamma, now this will be slightly different in this case. Now remember that this at what condition we can write it in to be equal to XB. That's the thing here. Now you can write it to be equal to XB. In fact, you cannot write it to be equal to XB, because already Henry's law, we know that it cannot be proportional to XB. It is some constant into XB, and that constant we have to measure experimentally. Now what it means is that when I have a very dilute solution, so it is already ideal solution. That's why I talked about a departure in Raoults law. By incorporating a term arbitrarily, which is activity, and trying to connect this activity with mole fraction, which is for the real solution. So all this discussion on activity is on making it as an effective mole fraction was to see the real life situation. So this is a real situation, which is a deviation from ideal behavior. And remember, this was an approximation in the Raoults law. We could write one more line here, that PA by PB was taken to be PA by P total, which is the mole fraction. So that is basically Raoults law here. And now we introduce activity that will explain everything for the real solution. So from ideal solution we are going to real solution, and the way is that from ideal solution, if we go to real solution, so we see that this real solution, you have to always write it in terms of activity. Ideal solution, you could write it as activity, the mole fraction, and the activity is connected to the mole fraction through the activity coefficient. But of course these two will be equal for a dilute solution, when actually your mole fraction is almost equal to 1. Now from the solutes perspective, we know that even for a dilute solution there is a problem. So we are saying that already we know that in that case we have to use AB into XB. Now think about it. If I say that gamma B is tending to 1 when XB tends to 0. XB tends to 0 means actually it is now a dilute solution. Remember that for a dilute solution means it's a mostly solvent and very less amount of solute, which means XA tends to 1 and XB tends to 0. So if we impose that condition, now if I also say that gamma B tends to 1, then we have a problem. Then actually we have Raoults law, which is already wrong, we know. So either we can write that gamma B tends to Kb, then it is fine. Then it is again behaving as an ideal dilute solution, which is the Henry's law. So we can write, instead of activity, that it will be nothing but, we can write it as before, gamma b, plus we can write it as, we could actually define it in a slightly different way. Instead of writing it like this, we can actually use our old convention that I'll not use gamma b tends to kb, but rather I'll just write it as ab is equal to gamma b into kb into xb, so that I can say that when this xb tends to 0 for an ideal dilute solution, this gamma b tends to 1. Then I have satisfied everything. So then if I just put the value of activity here, so I'll have RT ln gamma b plus RT ln kb plus RT ln xb. So then we have basically satisfied everything, and you see that the clear difference in the definition, that how will you write it. You know that there you have it's a little bit confusing that you have two situations. So one is actually you have only one situation, but you are looking at from two perspectives. One is solvent's perspective and what is solutes perspective. And we already said that when we have a ideal solution, let me again write it. Ideal solution means which will show some ideal behavior. Now this ideal behavior, just like in ideal gas, when you see the ideal behavior when the pressure of the gas is too low, which means the density is very low. The same thing we are seeing here. So density of what is low? That is basically the solid's density is low, solid's mole fraction is low. So in a limit of dilution, any real thing should behave as a ideal system. So in the limit of if it is a fairly dilute solution, or we can write it as if it is an ideal dilute solution, so then we can say that XA tends to 1 and XB will tends to 0, because that's the condition for dilute solution. In that case, we can actually recover our Raoults law by writing XA into gamma A into XA, and then we can write our this other equation, which is the Henry's law, as activity of B. It will be nothing but gamma B times Kb into Xb. So in either case, you can see this activity is actually proportional to mole fraction, or it is telling some effective mole fraction. But again, keep that in mind that this gamma is not a constant. It's basically it will vary with respect to the concentration. Similarly here, the Kb is taking care of everything. Now you can write it in two different ways. Either you can include the Kb inside gamma, and then you can say that the gamma is actually varying with respect to Xb. That way also you can think of. And now the point here is that we introduce this part in discussing reaction quotient, in the sense that we need to now write as we know that what is the reaction quotient? It is nothing but the differences in the pressure, and we wrote it as Pb by Pa for a reaction which is going like A to B. But we'll now use a general equation and ask this question, how to write this reaction quotient. Now this we got by writing the mu in terms of the pressure, like Pb by Pa. But now what are we going to do? We are just going to write it as instead of writing it in terms of pressure, we are going to write it as mu 0 plus RT ln activity of the situation. By the way, when I write it as activity, so when I use this equation, of course you have to, in real life situation, you usually connect it to the concentration, because this mole fraction is also connected to the concentration, and usually you connect it to molality of the solute, and there are equations how you connect the mole fraction to the molality, and then you just write the Henry's law in terms of just Kb into B, something we discussed, and then we'll replace the activity with concentration, but that strictly is valid only for the dilute solution limit, when the solution also behaves ideally, with respect to the solid perspective as well. But we often use it even for any concentrated solution. Also we often use this reaction quotient as the ratio between the product versus the reactant, and that's not very correct from the thermodynamic point of view, because as we see that the energetics are not very correctly explained. So that's why we wrote this equilibrium constant. When we wrote it, we specifically said that it is a thermodynamic equilibrium constant. Whenever you are using the thermodynamic equilibrium constant, you have to be very careful. One is that you have to divide it by the standard state pressure, and secondly, you have to, for a real system, you have to always consider the activity and not the concentration. So that way we'll we will keep this notation for future perspective. Now in the next section we are going to discuss how we can actually consider the general case, something like we already discussed, like if I have a stoichiometric equation where the stoichiometries are not necessarily 1, and then what will be the general expression of the reaction quotient or the equilibrium constant for this equation. That's what we are going to discuss now.